and this is your spatial average. Okay, this is your spatial average. Let us put a subscript x to denote that this is spatial average. Okay, so spatial average will be a function of time. You have integrated out the spatial variable, so it will be a function of time. I hope this is visible. And then a temporal average is something that you integrate over time and average the time out. So, temporal average will be a function of space. Okay. The ensemble average is basically, so if you knew the probability density, this is literally the expected value of u prime, and so you will write it as p of u prime du prime, where this is your PDF. Okay, this is your probability density function of the of this variable. Okay, and in some sense this is the true average, because this is the average that you would obtain by considering same experiment with multiple of its realizations. A realization in probabilistic sense is basically a sample that you have drawn from the whole sample space. Okay, for example, there are coin tosses. Let's say you're doing two coin tosses, you're tossing two coins, then h comma t, heads comma tails, is one realization of all the sample space that you can possibly have, of the whole space of all the possible outcomes. Okay, so we said that so for steady turbulent flows, what we say is that your time average is equal to this ensemble average. For homogeneous turbulent flows, by the way, this true average, which is the ensemble average, this can be a function of both space as well as time. Okay, because this probability density function that you have, this is basically the value of u prime at x comma t. Okay, so this ensemble average can be a function of both x and t. Okay, so for homogeneous turbulent flows, what we say is that the spatial average is the same as the ensemble average. Okay, now there is another class of flows which are called isotropic turbulent flows, and in the isotropic turbulent flows, what we have is that, as the name suggests, that the flow is isotropic in nature. The turbulence is isotropic in nature. You may not have mean flow that is happening in all directions. You may have a mean flow that is, let us say, predominantly in only one direction, but the turbulence is isotropic in nature. And in this case, basically, you don't have any directional dependence. So, for example, if you computed, let's say your u is u1, u2, u3, and x is x1, x2, x3. Okay, and so if you computed, let us say, del u1 by del xi, and you took an average of this, then you will see that this is actually equal to the average of this quantity, and this is also equal to average of this quantity. So the idea is that any directional quantity that you can think of, they all will be same. Okay, additionally, what you will see is that u1 prime, u2 prime, and u3 prime, okay, they will be similar in a very definite sense. So, for example, we have shown in the last class that technically the average of turbulent velocity is 0, because this is from the definition of Reynolds decomposition, that you have u as this, and from here we saw that the ensemble average of turbulent velocity is 0. Okay, so in isotropic turbulent flows, it's not enough to just say, okay, mean of u1 prime, mean of u2 prime, mean of u3 prime will be same. Of course, they will be same and they will be 0, but there is additional quantity that you can define, which is called the turbulent kinetic energy, and the definition of turbulent kinetic energy is, it is basically ui prime by 2 and an average of this. Okay, and it is this quantity which you can say this is u1 prime square plus u2 prime square plus u3 prime square by 2, and in for isotropic turbulent flows, u1 prime square will be equal to u2 prime square will be equal to u3 prime squared. Turbulent kinetic energy. So, this is essentially the kinetic energy when you do the Reynolds decomposition of kinetic energy. So, kinetic energy will be basically this quantity per unit mass. Okay, all of these quantities are per unit mass. So, kinetic energy per unit mass will be this quantity for a fluid flow. You will substitute the Reynolds decomposition here. Okay, let us say you write it like this. Now, let us look at mean kinetic energy. So, you take a mean operation of this, and so what you will get is that this is equal to this quantity plus you will get mean of u times mean of u prime. You will get 2 times mean of u dot mean of u prime. What is mean of u prime? 0. So, those two terms will eventually drop out and you will be left with this one. Okay. So, the mean kinetic energy can be looked at as kinetic energy of the mean. So, this is kinetic energy of the mean flow plus a turbulent kinetic energy. Okay. So, this is how you can look at the kinetic energy, mean of kinetic energy of a turbulent flow is kinetic energy of the mean flow plus a turbulent kinetic energy, and when you define that, there you will see that all of these quantities are same. Let us write them as u prime square, and so your TKE will be simply 3 u prime squared by 2. Okay. So, these are some quantities which are very useful when we define turbulent flows. There are additional quantities which are useful, but these are, let us say, required for our next discussion. And in this course, if you see any question of turbulent flows, okay, until unless otherwise mentioned, we will assume that our turbulent flow is steady, it is homogeneous, and it is isotropic. Okay. So, all of the times we are going to look at homogeneous, isotropic, steady turbulent flows. Okay. Very specific. Yeah.
Can you explain what is isotropic? You said that the flow can be not isotropic, right?
I did not say yeah, flow can be non isotropic. So, what I said here was that mean flow. So, when you say isotropic turbulent flow, it does not mean that your mean of u1 equals mean of u2 equals mean of u3. That is not what I am trying to say. I am trying to say that the turbulence is isotropic. Okay. Turbulence is random fluctuations riding on top of a mean flow. The mean flow can be literally a flow in just one direction, and the random fluctuations on top of that are isotropic. So, when we say isotropic turbulent flow, it is a property of the turbulence in the flow, it is not a property of the flow. That is what I am trying to convey here. So, here what we try to say is the gradients that you have, they are also, the mean gradients are also equal in all directions. Okay. So, here I am assuming that you do not have any gradients, basically you do not have any gradients in your mean flow. Okay. When I say this, technically you can hold this quantity for, you can write this equality for non homogeneous turbulent flows also, but as I said, for steady homogeneous flows, all of our discussion holds, okay, as far as this course is concerned. Okay. And if it is not mentioned explicitly in a question, you can write that we are discussing you are deriving the result for a homogeneous isotropic turbulent flow. Okay. And from here we move to a very important concept of Reynolds averaged Navier Stokes equations, or RANS as they are called. Okay. The Reynolds averaged Navier Stokes equations, again everything is all incompressible. So, basically what we try to do is, for the full velocity field, that is this u, we know the governing equations. Let us say you have the continuity equation and then you have the momentum equation. Okay. For the full velocity fields we have this. What we try to do is, okay, let us take an averaging operation on these equations. Let us do an ensemble average of these equations and let us see if we can try to find the equation for this. Okay. Now, why is the equation for this very important? Those of you who were present in the last lecture, you would recall that, let us say you have a turbulent channel flow, and in that case you have very random perturbations in the velocity profile. Okay. But what you will see is that there is a mean or an average that you can define if you consider multiple of its realizations. And from this mean or average, we derived the practical conclusion that the force on the walls due to a turbulent flow is much larger than the force on the walls due to a laminar flow, because the gradient at the walls is much higher. Okay. We derived this conclusion that gradient at the walls is much higher for a turbulent flow compared to a laminar flow. So, this quantity, knowing this quantity, is of high practical interest in turbulent flows. Now, if it is of high practical interest in turbulent flows, we know the governing equations of overall velocity. So, it is natural to proceed in a direction, okay, let us try to find out the equation for this quantity. But as you will see, it turns out you can't derive a equation completely for this quantity, it will depend on this eventually, because as you can intuitively guess that the averages will depend on, the average here will depend on how the turbulence looks like. Okay. So, that is the whole point of this discussion of Reynolds averaged Navier Stokes, that we are trying to derive an equation for the practical quantity of interest. So, basically let us try to consider it one by one. So, here you have this. So, this means substitute the Reynolds decomposition. Okay. And so, from here you will get okay. Now, this averaging operation, as you can see, the way we have defined this averaging operation, it is an integration with respect to the PDF of that particular quantity. Integration is commutative. The PDF, the integration is over all the samples. It is neither over space, the integration is neither over space nor over time. So, if I had, let us say, del by del x of here outside the averaging operation, I could bring it inside the integral, because these are just samples of that particular random variable. Okay. So, that means this quantity is the same as del dot of this quantity, and this quantity is the same as del dot of this guy. Okay. Now, mean of u prime is something that we have derived there as 0, and mean of mean is going to be simply the same thing, mean. So, the continuity equation is something like this for your mean flow. So, okay, we have one equation that says that, okay, if your overall flow variables, they satisfy the continuity equation, then your mean flow also satisfies the same continuity equation. Okay. Now let us try to derive what happens here. So we have this. Now as I said, you can take the time derivative and integration, or spatial derivative and integration, and they will basically commute. So that means this is equal to del by del t of simply this. Just break this u into mean of u plus u prime and you will get this. Okay. Let us look at the second term. Rather than second term, let us first look at the easier linear terms. So we have this guy, and when you take an average, so rho is constant for us, we are dealing with incompressible flows. So this is simply gradient of mean pressure. Okay. So pressure also we are decomposing just like velocity. There is a Reynolds decomposition, there is a mean plus there are fluctuations. Okay. Same thing happens for your viscous terms. Viscosity is not varying for us, we are looking at very simplified cases. So this thing is okay. And now let us look at the problematic term. So let us look at the problematic term, and instead of looking at it direct in the direct notation, let me convert it into index notation, and we will have this. Okay. And so here also I can do here also I can do this, and so let us try to break it down. So what will we get? We will have a mean of uj del of mean of ui by del xj. Okay. What about the cross terms? So you will have a mean of uj prime times del by del xj of mean ui. Mean of uj prime is 0. Okay. So you will have a mean of uj prime del of mean ui by del xj. This guy is 0. Similarly, you will have a mean of uj del of mean of ui prime by del xj. This guy is also 0, and you are left with uj prime del ui prime by del xj. So that means when you take the average of this nonlinear term, you end up with two terms, and those are mean of u dot something like this plus a mean of u prime dot grad of u prime. Now let us substitute them here and see what we get. So this gave us that del dot of mean is 0, and this gives us what? This gives us what? Del by del t of mean of u plus mean of u dot grad of mean of u plus a u prime dot grad u prime minus 1 by rho grad of mean of p plus nu del square mean of u. Now if you do not look at this term, then if you do not look at this term, then you can see that our system is closed. If this term was not there, if this particular guy was not there, then you see the whole equation is in mean of pressure and mean of velocity only, and you have mean of continuity. So the equations would be same as your Navier Stokes equation. Okay, just instead of velocity you would have equations in mean of velocity, and everything would be fine. Turbulence would not be a research topic. Why are you clicking pictures when I have explicitly asked you not to? Okay. If there's something that's not visible, you can tell me, maybe we can help, but please don't click pictures. Anyways, you'll have the video with you, lecture video with you. So you have mean of velocity in the equation if you do not pay attention to this term. But of course, this term is there. This annoying term is there, just like this annoying course in your 7th semester. So you can't really model any mean term just by itself. Okay, you can't model any mean term just by itself. You need the information of these fluctuations to be able to model this mean flow. And it's not just that you need to model the fluctuations, it is particularly you need to model this quantity, the average of a multiplication of fluctuations. Average of fluctuations themselves is 0, but average of multiplication of these fluctuations is not 0. Technically, in probabilistic terms, you can think of it like you have to evaluate a correlation between two terms. Okay, when you take an average of, let us say, two random variables u v, it is basically expectation of u times v. Okay, so if these are two random variables, then you will have to consider the marginal the uh, double probability. So this will be basically integration u v p of u comma v. So the joint probability distribution is something that you will have to entertain for this kind of a average. Okay, joint probability p of u comma v is not in general equal to p of u times p of v. When does this equality hold? When they are statistically independent. Do you expect that the velocity fluctuation and its gradient will be statistically independent? Of course not. Okay, so eventually you are left with something like this, and this is the crux of whole turbulence problem, and this is called the closure problem in turbulence. People have given it a name. Sounds like someone went through a breakup or something. So this is a closure problem. Okay, and the idea here is that you cannot model your mean quantities just by themselves. You need some fluctuation information. Okay, and this is, I mean, people have given it fancy names, but this is a problem in all of mechanics, in all of physics. The idea is you have something which exists at very small scales, and a lot of those things are giving way to an emergent phenomena at large scales. And effectively what you are saying is it is impossible for me to model all the large scales by completely ignoring small scales. Okay, just like even if you look at your Navier Stokes equation, we could not write the whole equation until unless we brought in the Stokes hypothesis, where we introduce these constitutive parameters of viscosity. What is viscosity? Viscosity is trying to capture the molecular information. We could not derive even a full governing equation without modeling that molecular information somehow. Okay, and the same type of modeling or similar type of modeling you need to do in all kinds of these problems where you have a hierarchy of scales. When I say hierarchy of scales, it means that flow is not generally existing over a one particular length scale. If you look at turbulent flow in a room, the length scale of the turbulent flow is not just the dimensions of the room, it will vary. Okay, you will have multiple length scales in that turbulent flow. You will have length scales of order meter, centimeter, millimeter as well. You will have gradients which exist over all of these length scales. Okay, and what this equation or what this closure problem is trying to tell you is you cannot model the flow at a meter length scale by ignoring what is happening at a millimeter length scale, let us say. You cannot model it. Okay, you cannot solve for it. You have to model what is happening at the millimeter length scale. You need to know some information of that millimeter length scale, and only then you can derive or you can find a solution for this type of an equation. Okay, so towards modeling this closure, term, this is also called a Reynolds stress term, and the reason for calling it that is very evident. And the idea is that you have this guy. So you have uj prime del by del xj ui prime, not a star. Okay. Now if you focus here, the whole velocity satisfies continuity and the mean velocity also satisfies continuity. So if del dot u is 0 and del dot u prime is 0, oh, del dot mean of u is 0, this would imply del dot u prime is also 0. Okay, you substitute u as mean of u plus u prime, both are 0, so del dot u prime will also be 0. So that means del u prime, del u j prime by del x j will be 0. So I can bring this j prime inside and I can write this term as del by del x j of ui prime uj prime, which is nothing but divergence of a tensor. Let us say, let us write it like this, del dot of r, just like we wrote this term. If you recall, we got this term by writing it as divergence of your stress tensor. This is another type of a stress tensor where this r is called, this r is basically mean of ui prime uj prime, let me write it in index notation, and this is called your Reynolds stress. And so just writing this equation in a more nicer form, we will get del by del t of mean of u plus all the terms as it is for Navier Stokes equation, but just for mean quantities, plus an additional problematic term, and that is this del dot of r. Okay, and its modeling. So modeling of Reynolds stress is required. Modeling of r is required to solve mean of u and mean of p. Okay, and this basically gives you some picture of what you can expect in the further course in fluid mechanics, which will be modeling of turbulent flows, which is offered in our department, and you can consider taking it. Modeling of turbulent flows. As you see, it is a separate course of itself. So there is no way I can fit all of those things in a single 5-minute, 10-minute remaining lecture. Okay. Now, for modeling these turbulent flows, what you need to know is the hierarchy of scales basically. So, the hierarchy of scales is something that you need to know. What this hierarchy of scales means is, let us look at a very sketchy picture of a turbulent flow. Let us say you have a flow that is coming in like this, and if you focus on it, okay, if you let us say were to observe some density gradients in it, something like you would have seen, let us say you are standing on a signal and you have seen flow coming out of automobiles, okay, when they are hot and there is air rising from them. So you see the density gradients and you see them fluctuating all over the place. You see a lot of spots that are coming in inside that flow. So something like that. Okay. Now what this hierarchy of scales means is, you would be able to observe some variation over a length scale of this size. You would be able to observe gradients over this size, and you will be able to observe gradients over this size as well. So you have multiple length scales that are involved in a turbulent flow. Okay, and some would say, okay, in a general flow, when you don't have, let us say, a single sine or a cosine, you would have multiple scales, and you would be right. The reason why we make this distinction in a turbulent flow is that all of these scales in between them also exist. So there is in a way a continua of scales. There is a continuum of scales that exist, and it is virtually impossible to literally solve for velocity at each of these scales separately by hand. So the only thing that we are left to do is, we have to give a statistical description of velocity at each of these length scales. That is, instead of looking at velocity at each point and at time, instead of looking at the probability density of velocity at each point in time, we have to look at probability density of velocity at a given length scale and time. Okay, that gives us a more general picture of turbulent flows. So, these hierarchy of scales is something that is required for you to be able to model turbulent flows. Now, let us look at what are these scales, what these scales I mean. So, let us say there is a turbulent velocity scale, I will label it with this capital U. This turbulent velocity scale is basically something like, so this we took, right, we defined this as u prime square. So, let me write TKE as k is 3 u prime square by 2. So, that means I can define a turbulent velocity scale as square root of 2k by 3. Okay. This is a scale of velocity. This is one scale of velocity. There are many scales of velocity that exist. This is one scale of velocity. Okay. And at this point, you will see that a lot of turbulence courses and turbulence discussion, they end up being exercises in dimensional matching. Whatever quantities you could conjure up and they would have dimensions of meters per second, that might be a scale of a turbulent flow. Okay. For you to know which scale is that requires a little bit of intuition and some study, but if you could conjure up any quantities which are relevant to a flow and make up meters per second, that's a velocity scale. At what length, you don't know, it's very difficult for you to know. So, this is one velocity scale, let us say. There is another length scale which is involved, which is often called the integral length scale of a turbulent flow. And the integral length scale is something like the largest scale of the turbulent flow. Okay. So, if you have a continuum of scales involved, then it makes sense to define a largest and a smallest, so that you can at least know the range in which those scales exist. So, they say L, which is the integral length scale, is the largest length scale of the turbulent flow, and so using these you can define an integral time scale which will be simply L by U. Okay. You can define an integral time scale which will be simply L by U. Okay. Now, similar to this, you can literally make up any scales, but for you to know which scale is that, what is the physical relevance of that scale, for that you can take the other course in our department, and that is called the physics of turbulence, in which these things are discussed. Okay. So, with this I will end up all the lectures of this course, and we will have our final quiz, and then we will leave each other alone. Huh?